Every 30 minutes, your leader crashes with OOMKilled. A new leader is elected, then crashes again. Writes are down for 2 minutes each cycle. You assume a memory leak, but the real culprit is a heap dump triggered by a ZooKeeper watcher. Let's break down what happened and how to fix it. Welcome to TheCodeForge. Before we dig into that production issue, let's cover leader election. Leader election is a distributed systems pattern where nodes in a cluster agree on a single coordinator to manage shared resources, avoid conflicts, and ensure fault tolerance. It prevents split-brain scenarios where multiple nodes act as master simultaneously. Before leader election, distributed systems used a single coordinator. If it died, the system was down until manual recovery. Automation introduced split-brain. 2 nodes both think they're the coordinator. Leader election solves this by ensuring at most 1 leader at any time. A common approach is using a distributed lock. Each node tries to acquire a lock with a TTL. The one that gets it becomes leader and starts a heartbeat to renew the lock. If the leader fails, the lock expires and another node takes over. Here's a simplified example in pseudocode. The tryBecomeLeader method attempts to acquire a distributed lock with a 30-second TTL. If successful, it sets itself as leader and starts a heartbeat to renew the lock. ZooKeeper is the old guard. Each candidate creates an ephemeral sequential Z node under an election path. The one with the smallest sequence number is the leader. If the leader dies, its ephemeral node disappears and the next in line becomes leader. Use Curator's leader latch. It handles session management and re-election. Don't reinvent the ephemeral node logic. Raft is a modern consensus algorithm. Nodes are in 3 states: leader, follower, or candidate. Leaders send heartbeats. If followers don't hear from the leader within an election timeout, they become candidates and start a new election. The candidate that gets votes from a majority becomes the new leader. Here's a pseudocode for Raft leader election. The start election method increments the term, votes for itself, and sends request vote RPCs to peers. If it gets a majority, it becomes leader. Leader election adds complexity. If your system can tolerate temporary inconsistency, use a gossip protocol or CRDTs. If you have a single writer that rarely fails, manual failover might be acceptable. For 2 nodes, use a shared disk or SDONITH. Only use leader election when you need automatic failover and you have at least 3 nodes. Even with leader election, split brain can happen if the old leader doesn't know it's been deposed. The solution? Fencing. When a new leader is elected, it must ensure the old leader can no longer access shared resources. In Raft, the term number acts as a generation clock. The leader includes its term in every request. Use a generation counter stored in a reliable store like ZooKeeper or etc. Before writing, check that the generation matches. If not, abort. This prevents split-brain writes. This is the same issue we highlighted at the start. Here's exactly why that happened. The leader node was running a ZooKeeper ephemeral-node watcher that triggered a full heap dump on leader election. The heap dump exceeded the 4 GB container memory limit, causing OOMKilled. A new leader would be elected, then crash again. Writes were down for 2 minutes each cycle. The fix was simple. Remove the heap dump trigger from the leader election callback. We also increased container memory to 8 GB as a buffer and added a memory limit alert at 70%. Never run expensive operations like heap dumps in the leader election callback. It's a critical path that must complete quickly. If your lock TTL is too short, the leader might lose the lock before it finishes critical work. If too long, failover takes forever. Start with 30 seconds and monitor. The article uses Curator Framework Factory New Client and Leader Latch, which require ZooKeeper 3.5+ and Curator 5x. In Curator 4x, the API is similar, but the package names differ slightly. Ensure your ZooKeeper version matches the Curator version to avoid runtime errors. The article mentions that Raft selection timeout must be randomized to prevent split votes. Here's a concrete implementation showing how to randomize the timeout between 150 ms and 300 ms, as recommended in the Raft paper. In production, leader election callbacks must be lightweight. Avoid expensive operations like heap dumps or database migrations in the callback, as they can cause timeouts or OOM kills, as shown in the incident. Offload heavy work to separate threads or queues. When things go wrong, start with network checks. Use curl to see the current leader in etc. Use ectl member list to verify cluster membership. Check resource usage on the leader node. Increase election timeout if leader flapping. Let's run through some common interview questions. How does Raft handle a network partition where the leader is isolated? The isolated leader steps down, majority elects new leader. When would you choose ZooKeeper over Raft? If you already run ZooKeeper for other coordination needs. What is the purpose of an ephemeral node in ZooKeeper? Automatically deleted on session end, enabling automatic failover. And a few frequently asked questions. What is leader election? A process where nodes agree on a single coordinator to avoid conflicts. How does ZooKeeper differ from Raft? ZooKeeper is an external service. Raft is an embeddable consensus algorithm. How do I implement leader election? Use Curator for ZooKeeper or etc's client for Raft. To recap, leader election prevents split brain by ensuring exactly one coordinator. ZooKeeper is mature but adds operational overhead. Raft is modern and embeddable. Always use fencing with a generation clock to prevent stale leaders from writing. And if you have fewer than 3 nodes, leader election is probably overkill. Ready to go deeper? Up next, quorum, R plus WN, then distributed transactions, and 2PC, then distributed locking. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.